determine whether the integral is convergent or divergent. Evaluate if convergent. The integral from negative infinity to positive infinity, x squared e to the negative x cubed dx. This is an improper integral, as we can see by the two infinite limits of integration. And since both limits of integration have an infinity, we're going to have to break this improper integral into two improper integrals. So this could be broken up into the integral from negative infinity to 0, x squared e to the negative x cubed dx, plus the integral from 0 to infinity, x squared e to the negative x cubed dx. Each one of these integrals is an improper integral, so we have to use the definition to evaluate them. So this is the limit as a goes to negative infinity, the integral from a to 0, x squared e to the negative x cubed dx, plus the limit as b goes to positive infinity, the integral from 0 to b, x squared e to the negative x cubed dx. We need to find an antiderivative of x squared e to the negative x cubed. So let's do that over on the side. So this is the indefinite integral of x squared e to the negative x cubed dx. We can let u be equal to negative x cubed. Then du is negative 3x squared dx. So we multiply on the inside of the integral by negative 3 and divide by negative 3 on the outside, or multiply by negative 1/3, however you want to characterize that. Negative 1/3 the integral e to the u du, which is of course negative 1/3 e to the u plus c, and u is equal to negative x cubed. And in fact, if one wanted to, the negative on the exponent will drop that factor of e into the denominator. It may help us down the line. Okay, so here's an antiderivative. So when we want to use that here, this tells us that we have the limit as a goes to negative infinity of negative 1/3 e to the x cubed. Now we're having a definite integral from a to 0, so we no longer need the plus c, plus the limit as b goes to positive infinity, negative 1/3 e to the x cubed from 0 to b. Okay. We evaluate the limits at the limits of integration. So first we substitute in 0, so 3e to the 0 cubed, minus, then you substitute in a, 3e to the a cubed. Similar thing happens for this second limit. We evaluate that antiderivative at the limits of integration. That's what the fundamental theorem of calculus tells us to do. All right. So our limit, a goes to negative infinity. 0 cubed is 0. E to the 0 is 1. 1 times 3 is 3. So this becomes negative 1/3. The two negatives make a positive. A is approaching negative infinity, so it's a very large negative number and getting larger. A is getting larger and more negative. So when you cube a negative, you stay negative. So I should have actually kept that negative there, I suppose. Okay. So a cubed is getting closer to, oh, pardon me. That's not what happens. If a is getting more negative, that's the exponent. So the exponent here is getting closer to negative infinity. Well, that means that e to that exponent is actually pulling back up into the numerator. So this is like saying, well, the 3 is still in the denominator, but e to the a cubed is getting closer to e to the a cubed, where a is positive, and going to positive infinity. So in fact, this whole thing goes to positive infinity. Now that we've taken our limit, we actually don't need it. And in fact, at this point, we notice that infinity minus 1/3 is going to be infinity, which tells us that the first integral diverges, which means that the whole integral that we started with diverges. We don't even have to evaluate that second integral. If either one diverges, then the whole thing diverges. So the integral from negative infinity to positive infinity, x squared e to the negative x cubed dx diverges.